process of steroidogenesis is one of the most important biological processes which are responsible for sustenance of an individual. This in fact is a very complicated process, and therefore there could be multiple ways in which there could be issues or abnormalities in these processes resulting in significant changes. The understanding of steroidogenic pathways is not only important for understand the various biological disorders associated with steroidogenesis, but also to have an insight regarding the various pathways through which various medicines acts, as well as physiology at fetal, maternal and pregnancy levels. Now we all know that the process of steroidogenesis starts from the bad guy, and we all have been knowing cholesterol as a bad guy for a long time. But what you need to understand is that cholesterol plays a central role as far as steroidogenic pathway is concerned. And from here we have the origin of the three key steroids that are the aldosterone, which is basically responsible for the sodium metabolism, cortisol, which controls stress, the regulation of blood pressure, and a huge number of activities including free water excretion, glucose, and in a way is a defender of the body. And finally, the androgens, which probably play a reasonable role in terms of various changes which happen during puberty, as well as the androgen levels in females, but the direct physiological role is not known. So which one of these steroids is the most important? Now, we'll often think that aldosterone probably is very important, and an individual will not survive beyond a couple of weeks if there is no aldosterone. Cortisol also is important, and there would be issues if we have normal aldosterone. The cortisol individual, deficient individual, will take some time because they have problems of hyponatremia because of free water excretion, hypoglycemia, but then it will not be as life-threatening as aldosterone. And DHEAS deficiency definitely may have certain issues like quality of life, memory, libido, but in the long run will not be life-threatening. So is aldosterone the most important steroid? The answer to that is big no. Whatever we need to know is that all the pathways of steroidogenesis of producing aldosterone, cortisol and DHEAS, if all of them are defective, even then a normal newborn is born at life. Because the whole salt metabolism is largely regulated by the placenta. There is not significant role of cortisol. If at all there is a role between 8 to 12 weeks of gestation, and the maternal passage of cortisol will be enough. Even though it is quite limited, it will be enough to really take care of it. And DHEAS deficiency clearly is not life-threatening. So the most important steroid compound which is essential for life is actually progesterone, because it actually inhibits the uterine contractility and therefore prevents miscarriages from happening. So if an individual is not producing any progesterone, and the placental progesterone is largely derived through the fetal actions, because placenta is in a way expressed through the fetus, there would be a situation that live birth is impossible. So contrary to our general belief, progesterone is clearly the most important pathway of steroidogenesis as far as this is concerned. Now, if you look at the overview, we all know that cholesterol is converted in three different organs. So in testis, it produces testosterone. In ovaries, we have production of estradiol. While in adrenals, we produce three groups as we discussed: the mineralocorticoid, the glucocorticoid and the androgens. Now, a lot of the enzyme activities are actually common for all three. There may be some difference as far as the isoforms are concerned, but these enzyme activities are pretty common in all three groups, and we need to have a production of DHEA at some point of time. Now, there is a complex pathway, and we're just talking about a basic overview before breaking it out into individual steps. We all know that cholesterol is pushed to the mitochondria using the STAR enzyme, where the side chain cleavage enzyme cleaves it into pregnenolone, which is then acted upon by 3-beta HSD to progesterone, which we discussed is the most important compound and the first biologically active compound as far as the steroidogenic pathway is concerned. Now, this progesterone is subsequently converted into DHEA, and then in different organs, depending upon the expression of enzymes, which will vary depending upon not only the age, the pubertal status, but also the cyclicity. we will have different steroids which are produced. So adrenals, depending upon the 11, 21 and 17 hydroxylase, will produce different sort of enzyme. Then we'll talk about how 17 hydroxylase forms the key branching point as far as the adrenal formation is concerned. And this 17 hydroxylase activity will really decide whether we have the production of aldosterone, cortisol or androgens in some part. The androgens are then converted into testosterone using 17 beta hydroxysteroid dehydrogenase, and there are multiple forms of this enzyme. 17 beta HSD3 uniquely for the testis really produces large amount of testosterone. So all these enzymes which are expressed in adrenals are also being expressed in the testis. In addition with, we have the 17 beta HSD which is responsible for testosterone production. So if you have an isolated defect in this enzyme, all the other steroidogenic pathway is intact, so there will be no feature of salt wasting or aldosterone excess in this setting. Finally, the testosterone is converted using aromatase enzyme into estradiol, and in addition to all the testicular and adrenal enzymes, we have the CYP aromatase which is responsible for aromatization, which is present in the ovaries. So this is a very simplistic pathway which says that a large amount of steroidogenesis is quite similar in different organs, but what we fail to understand is that there are different isoforms working in different parts. So 17 beta HSD, we may actually have beta HSD3 which is working only in testis. We can have 2 which actually is causing inactivation which is working in placenta. We have a different form for adrenals and ovaries. So these different isoforms will be regulated differently, and it is the differential regulation which is responsible for different production of steroids at different times of life cycles and in different aspects. Before going into the core part of steroidogenesis, just a few principles to understand. We need to understand that many of these enzymes are pleiotropic. So each of these enzymes can actually act on multiple pathways. For example, 3-beta hydroxysteroid dehydrogenase will act on a large number of delta 5 compounds, which includes DHEA, pregnenolone, 17-hydroxypregnenolone, and they will then be converted into a delta 4 compound. Similarly, 17-hydroxylase, 17-beta HSD can work on multiple pathways, and therefore we have a pleiotropic effects. Similarly, we also have a redundancy. By redundancy, what it means is that if one particular enzyme is different, maybe other enzymes can act on that pathway. An example, a classical example to that is the beta hydroxysteroid dehydrogenase enzyme, which have various isoforms which are differentially expressed as far as the life cycle and the organs are concerned. So you can have a differential expression in which is responsible for action. The most glaring example of this is the 3-beta hydroxysteroid dehydrogenase deficiency. Now when we discuss that, we will realize that in this pathway, all the delta 5 steroids are not converted into delta 4. So as far as androgens are concerned, we are stopping at DHEA. Now this DHEA has no androgenic activity. So theoretically, all males will be undervirilized. And if you talk in the theoretical sense, if there is no 3-beta HSD activity, all females would actually have no effect as far as their genitalia is concerned. But in reality, there is a concept of peripheral conversion using the 3-beta HSD1 isoform, which is present in different tissues like placenta, breast and other extra-adrenal tissues, which can convert this DHEA into androgens. And this conversion into androgens is actually a process is basically not enough to cause virilization in boys, but is enough to cause virilization in girls. So individuals with 3-beta HSD deficiency will actually have genital virilization in girls and under-virilization in females because of this redundancy effect. The other important thing to remember is that regulation of these steroids is different using either ACTH or different cofactors, and the balance between the cofactors often results in differential development of steroids in this perspective. The whole process of steroidogenesis actually starts from cholesterol, and it is the cholesterol flux which is also determinant for acute production of steroids, and the steroid production ultimately is through the mitochondria to a large extent. We'll discuss about the subcellular compartments playing a role subsequently. The cholesterol is pushed into mitochondria in an active form using a protein called STAR, which is steroidogenic acute regulatory protein, which enhances the process of steroidogenesis. In the absence of STAR, the steroidogenic pathway will be there, but it will act at around 14 to 15% of overall efficiency with STAR. Now, after they come to mitochondria and endoplasmic reticulum and ribosomes, we have the different enzymes which convert them to steroids. But what really brings the cholesterol into an adrenal cell? So the major amount of cholesterol that we get is through the circulating cholesterol, which LDL cholesterol acts on the LDL receptor and causing the influx of cholesterol. A minor amount of it is actually locally produced by the adrenal cells. And when there is excess cholesterol, it is actually stored as cholesterol sulfate, and there is a bidirectional process using the enzymes ACAT, which causes sulfation, and lipase, which causes release of free cholesterol from that perspective. Now, this whole cholesterol flux pathway is largely under the control of ACTH, which is adrenocorticotropic releasing hormone, which is the major regulator of DHEAS and cortisol secretion. And ACTH pushes the LDL receptor. It increases HMG-CoA synthesis along with effects as far as the ACAT pathway and the lipase pathway to increase cholesterol. It also acts at the STAR level and at enzyme levels to increase steroidogenesis. So the effect of ACTH on steroidogenesis is both acute, predominantly through providing more cholesterol in the cell, and through STAR in the mitochondria, and long term using increased activity of steroids. Just a point to remember that the secretion of aldosterone is not regulated by ACTH, and it is regulated via the use of renin angiotensin system along with potassium levels. So that's an important point to remember in this perspective. Now we all know that multiple compartments are involved as far as steroidogenesis is concerned, and first step obviously, as we discussed, is the pushing of cholesterol into the mitochondria using STAR, and there are 2-3 enzymes, side chain cleavage enzyme, which is the first enzyme which is important, 11 beta 1 and 11 aldosterone synthase, which are actually present in the mitochondria. And here they use an important cofactor, which is adrenodoxin reductase, which provides them with the electrons. And we'll discuss just later on that how this electron transfer balance is actually responsible for differential expression of various enzymes. Now, after the formation of pregnenolone, it is shifted to the endoplasmic reticulum, where CYP21 and CYP17 are there, which really are responsible for the conversion of these enzymes, and there is a shuttle of a lot of these metabolites in between these two organs with a final production of different steroids depending upon which pathway we are looking at. In the endoplasmic reticulum, there is a P450 oxidoreductase enzyme, which actually helps both 17 and 21 hydroxylase actions. And in situations of deficiency of this enzyme, we will have a very mixed picture, wherein we have features which are combining both 17 and 21 hydroxylase in this perspective. So now coming on to the core steroidogenesis, the first step obviously is the transfer of cholesterol. And we know there could be a slow process of cholesterol transfer which can happen in the absence of STAR. But once STAR is activated, this process becomes fast. So for a factory, we are giving much more raw material at a high speed. So output would basically increase. But even if there is no STAR, as we discussed earlier, around 15% of steroidogenic activity will be there. So these individuals will have less steroid, but will not classically be having zero steroid as in some of those severe forms of enzyme defects. So theoretically, if you have a STAR deficiency, then there will be no production of aldosterone, of cortisol and androgens. But because there is some amount of action which is there, some activity, residual activity is there. The other thing to remember is that if there is no STAR, this rapid transfer will not be there. So cholesterol will tend to accumulate in the cytoplasm in the form of large vacuoles. And after a level of these vacuoles, the cells will actually be destroyed or burst. So this is the second hit. So STAR deficiency classically has a 2-hit model, In the first hit, the steroidogenesis is defective, so we have 85% reduction, which is not lethal. But with time, when the cells are active, those cells accumulate a lot of cholesterol, which actually is evident in the form of the adrenals, which become large in what is known as congenital lipoid adrenal hyperplasia. And there will be large vacuoles, clear cells which will be visible on the microscope, also can easily be identified. This is the second hit, and the rate of steroidogenesis will determine which cells will be affected first. So for example, fetal testes are highly active. So if the fetal testes are highly active, they will produce a lot of these cholesterol vacuoles and they will be damaged in utero, effectively resulting in utero testosterone deficiency. Therefore, males with star deficiency will present not only with salt wasting, but also with an external genital appearance resembling a female. So if you have a situation in which you have a girl with salt wasting and gonads which are there, star deficiency becomes an important differential diagnosis to consider in the situation. However, in females, there will be no effect because even in the absence of estrogen, you will have a lot of changes which will happen. So there will be a normal female with no gonads along with salt wasting will be the classical presentation. The other thing to remember is that because a lot of these aldosterone and cortisol producing cells are not as active in the fetus, so at birth there will be some activity which will be there, and once they become more active postnatally, gradually those cells will become destroyed and we will have features of salt wasting. So classically, children with star deficiency will have a delayed presentation of salt wasting as compared to those who have 21 hydroxylase deficiency, where it typically occurs between 2 to 6 weeks of life. So there have been cases which have been reported into few months or even up to a year of case. So if you have a delayed onset of salt wasting, you should always consider star deficiency. Diagnosis is simple because all precursor steroids starting right away with pregnenolone, progesterone, 17-hydroxyprogesterones, everything will be low. Diagnosis will become easy. The close differential to this is adrenal hypoplasia congenita, in which basically there is no steroid being produced because there is no adrenal, but it's an X-linked disorder, generally not associated with disorder of sexual differentiation, so it will have a male appearance. The only issue there is that adrenals will not be visualized, they will be small, while lipoid adrenal hyperplasia will have large adrenals. Another very important thing to remember is regarding the pubertal development in females. Now, the ovaries are quite quiescent as far as the fetal period is concerned in terms of estrogen production. So they will not have the second hit happening. And the unique aspect about ovarian development is that with every cycle we have different follicles which are being formed. So those follicles to begin with will produce estrogen. Therefore, some amount of feminization, breast development, and even vaginal bleeding can happen. Now, by the time we have the time for progesterone production, there will be so much cholesterol laden in those oocytes that they will burst at that point of time. So there will not be a progesterone action. So this is typically an ovulatory cycle which will happen, and with time those follicles will be ruptured and will have problems later on. So typically, girls with star deficiency will present if they have a milder form of defect. Severe form will present as salt wasting. The milder form will present with anovulation, delayed puberty, / amenorrhea versus even infertility, depending on the spectrum. So star deficiency is something we need to consider in that possibility. Having said that, the next step is the chemical conversion, and just to provide an overview of in this regards, we have a substrate. Which substrate, if there is an electron transfer to that substrate, it actually gets oxidized into, reduced to that product. And there could also be a reverse process in which the electron is actually transferred to the donor where it becomes oxidized. And this pathway often of reduction and oxidation is usually reversible and determined by the substrate number, the substrate amount, as well as the situation of electron donors in that perspective. So if the electron donors are at a high level, we will have a greater process of reduction, while if recipients are at a higher level, we will have more oxidation, and this really plays an important role in differential expression of steroids at different zones of adrenals and different time frames as far as life is concerned. The most common donor is NADPH and receiver is NADP+, and there are mediators which are working in this pathway are the oxidoreductase and adrenodoxin, as we discussed. So this electron transfer, adrenodoxin reductase, plays an important role in the side chain cleavage enzyme and CYP11, and both of them are located in mitochondria, while this oxidoreductase has action as far as the CYP17 and the CYP21 pathway is concerned, and they are regulated in the endoplasmic reticulum. Just a brief word about the different enzymes which play an important role in that perspective. We have two groups of enzymes. One is the P450 oxidase and the other is hydroxysteroid dehydrogenase. The P450 oxidase is a heme enzyme and it absorbs the peak light at 450 nanometers. It is actually not specific for adrenals. It is present in the liver and it helps in metabolism of number of external environmental factors including xenobiotics and steroids and sterols and all sort of pathways. Importantly, P450 oxidase systems do not have isoforms, while hydroxysteroid dehydrogenase have a lot of isoforms. This has relevance because phenotypic expression in 21 hydroxylase or 11 hydroxylase or aromatase will vary only depending upon the amount of expressed amount of that particular enzyme. While for hydroxysteroid dehydrogenase, there will be different isoforms which are represented in different part of the body, causing a different myriad presentation, as we will discuss subsequently. Traditionally, the P450 oxidase have a unidirectional effect, while HSD can act both ways. So 11 beta HSD can convert cortisol into cortisone in places where it wants to protect the mineralocorticoid pathway from the effect of glucocorticoid, or activate cortisone to cortisol in those places where we actually want to augment the glucocorticoid effect. So there is a bidirectional effect, and this is quite significant to understand. And the classical example of P450 include the 5 enzymes: side plane cleavage, 11 aldosterone synthesis, 11 beta hydroxylase, 21 hydroxylase and aromatase. While HSD, we typically have 3 beta HSD, which is converting delta 5 to delta 4 compounds, 11 beta HSD, which plays a role in conversion of cortisol to cortisone, and 17 beta HSD, which converts androstenedione to testosterone, and a lot of testosterone estrogen crosstalk will be important in this regards. So the first important enzyme which acts in this pathway is the P450 side chain cleavage enzyme, which basically cleaves the side chain and results in the production of pregnenolone, which is the first important metabolite of this whole pathway. P450 side chain cleavage is the first enzymatically regulated pathway and the rate limiting enzyme in this whole process. And this is regulated by the CYP11A gene. So our pathway has now started to form. So we had cholesterol, which under the action of side chain cleavage and star, and both of them are quite synergistic, and the effects of deficiency of both of them is very similar, that we have a lot of cholesterol accumulating and we'll have lipoid sort of picture on adrenal hyperplasia to production of pregnenolone. There, however, is a crucial difference. Star enzyme is not expressed in placenta. So placental progesterone formation is not going to be hampered in star deficiency, while side chain cleavage enzyme is expressed in placenta. So if you have complete deficiency of P450 side chain cleavage enzyme, it is incompatible with life because there will be a risk of miscarriage. We have now been observing a few milder form of this disease which present with a situation which is quite similar as star deficiency, but complete deficiency is clearly incompatible with life. The next important enzyme, and I would say one of the most important to decide the fate of the cholesterol that started off, the whole story will actually decide it here only, is the P450 17 hydroxylase enzyme. And there has been a huge confusion about this enzyme because often it was considered that there are two separate enzymes in this group. One is the hydroxylase and the second is lyase, because there are differential actions of different steroids in different forms. But now we know it is the same enzyme, But depending upon the environment, and in particular the electron donor situation, will decide whether only one part of the activity, which is 17 hydroxylation, will be done, or we will have both the activities. So traditionally, CYP17 hydroxylase converts pregnenolone and progesterone into 17 hydroxypregnenolone and 17 hydroxyprogesterone. If the environment is conducive, we will have the second action of 17 lyase, which then converts 17 hydroxypregnenolone to DHEA and 17 hydroxyprogesterone to androstenedione. And this whole environmental process is under the control of the oxidoreductase enzyme. And it's very important to understand here is that differential action of the hydroxylase and the lyase enzymes will result in different expression of steroids. So this is actually the branch point of steroidogenesis. So pregnenolone is converted via hydroxylase action into 17 hydroxypregnenolone. If there is lyase action, it is converted into DHEA, which ultimately is converted into testosterone. While if there is no lyase, it can then be acted upon CYP21 and 3-beta to produce 11-DOC and then subsequently cortisol. If there is no hydroxylation or lyase, the 3-beta HSD pathway takes over and we will have progesterone, and from progesterone, aldosterone is produced. So if both hydroxylase and lyase are present, it will produce androgens. If both hydroxylase and lyase are absent, we will have aldosterone which is produced. But if there is hydroxylase but no lyase, it is the cortisol which is being produced. So just to summarize the role of differential expression of CYP17, if we have a situation like glomerulosa cell where there is no hydroxylase, no lyase, the prime product is aldosterone. So in our fasciculata, we'll have hydroxylase but no lyase, it will produce cortisol. Well, finally in the reticularis, there is both hydroxylase and lyase producing DHEA. Now this is a simplistic version of a very complex process, but it really helps us identify the different zones. What we need to understand that these different zones will interdigitate and they will have differential expression of cells in this regard. So we need to be a bit careful, and the electron availability in this situation will actually decide about which way our pathways are going and how they will work from that perspective.